In this Mathematica session, we're on to episode 3 of Discrete Math, in which we'll be studying elementary number theory, and in particular, divisibility, modular arithmetic, remainders, and the floor function, and all that goes with that. So you can see we'll be proving some things too. If you're interested in that, then stay tuned. Okay, so our first problem says find the unique factorization of the integer 27,720. Okay, so what that means is to find the canonical factorization, as in prime 1 to the power of the exponent, prime 2 to the power of its exponent, and so on and so on. But how do we do this? Well, we can just perform some trial division. So you can see that it's even. You can even see that it's divisible by 10. All right, so in other words, 27,720 is equal to, put equals because this will actually execute here. 2772 times 10. Okay, so we got part of this done, but I can also see that 2,772 is even. So half of that, well, let's just calculate that. All right, so 2772 divide 2. Okay, so that's 1386. So this is equal to 2 times 10 times 1386. Okay, now I can see that 1386 is also even, so let's just calculate what is half of that. Okay, 693, so we found another 2 in this, and then I'll just put 693 here. Okay, but now obviously 693 is divisible by 3, right? Because the sum of the digits is divisible by 3, because each of the digits is divisible by 3. So we can divide this one by 3. So let's do that. 231, but now I can see straight away that 231 is also divisible by 3, so we may as well make that a 9. Okay, and so we get 77. So I'll put the 9 in here, and then we have 77 there, but 77 is clearly 7 times 11, and both of those are prime. Okay, so 7 times 11. Now, that's a factorization of this number, but it's not the canonical factorization we're after. Okay, because we still have to factorize the 10. So the 10 is 2 times 5. Okay, and then the 9 is 3 times 3. Whoops, what did I do here? I hope I still get this right. If I so 2 times 5. Just check that, false. I've got too many 2's probably. Okay, so there is a factorization in terms of primes, but what we actually want is the factorization in terms of power. So how many 2's do we have? Well, we've got 3 of the 2's. And then we've got 2 of the 3's. So we'll put those next because they're the next least one. And then we've got 5. We have 7 and we have 11. All right, so we'll double check that. Okay, now this here is the canonical factorization of the number. So there we go. Any questions? No? All good, guys? Great. Thanks for the thumbs up. Yeah, just speak up when you feel the need or the want. Okay, so we'll just give some space here, and we'll have a look at the next one. Now, the next one asks us to evaluate 58 div 11 and 58 mod 11. All right, so div is not a typical number theory term. I think it's just particular to this book. But what they're referring to is when you divide 58 by 11, and then you look at the floor of that, or the greatest integer less than or equal to that. Okay, so what I'll do now, of course, I can calculate the floor in the software, right? But I don't really want to be doing a lot of software calculations in this. I'm mostly using this to type. But I'll just show you what it would be if you were doing it on the calculator, right? So 58.0 divide by 11, and let's see what this number is. Okay, so you can see that if we punch this in the calculator, we would get 5.27 and so on. It looks like it's recurring with 27. So the floor of that, we'll just take the integer part of it, which is 5. All right, so in other words, what we've got here is that 58 div 11 is equal to 5. Whoops, not 45, 5. Got fat fingers today. Okay, now how about 58 mod 11? So to get the remainder, and this is the remainder, it's the least non-negative remainder when you divide 58 by 11. Now, of course, I can also calculate that with my computer here, but what you do is you just take, and I'll just do this calculation because, again, this is one that you can do by hand or by computer or by calculator. So what we do is we want to represent 58 as the quotient 5 times 11 and then plus our remainder, where the remainder is between a 0 inclusive and up to 10, which is 1 minus 11. All right, so how do we actually calculate this? Well, what we want to do is perform a subtraction. All right, so I'll take the 55 here to the other side of the equation, and that will be equal to the remainder. Okay, so in other words, just this, and you can see we get 3. All right, so then we'll say that 58 mod 11 is equal to 3. But I'll point out that this is speaking as if this is a function that returns a unique remainder, right? But remainders are generally the whole collection of numbers satisfying the congruence. All right, so I'll just give you an example here. So now if I would use this function mod here, we'll just write 58 and then 11, and you see it gives me 3. Okay, so this is a function here that I've used to calculate that. But another number when I divide by 11 will also give me 3. So there are multiple remainders when I divide by 11. In fact, so 11 plus 3 is 14. So let's just try that. Okay, 14 also gives me 3. So I can write then that in mathematical language that 14 is congruent, and for congruence you put 3 horizontal lines, right? But here I'll just put an equals for it. You know what I mean? So 14 is congruent to 3 mod 11, right? But there are infinitely many numbers that are congruent to 3 modulo 11. Okay, any questions? Yes, Jinyu, do you want to say?
Can I ask a question about the first question?
First question up here?
Yep.
Yeah, go.
One of the questions says that find a unique factorization about something, and are we required to write the whole step or just the final solution?
Is it an assignment question or is it something else?
Or maybe both the assignment and final examination?
Okay, so if it's the final examination, what I would do is show a few intermediate steps for getting that unique factorization. Right, now there are lots of different ways. The most straightforward would be to use trial division, right? So if you just show at least one step and then the final answer, you put it in order like this, least prime to greatest prime, showing the respective powers. Like I could even put to the power of 1 here, right? And so on. So yeah, just 1 or 2 steps, just so that the person who is marking your assessment is confident that you understand what you're doing, but don't go all out, I would say. Just enough that it's clear that you actually did the work rather than just punched it in the computer. Like for example, I'll just show you. So I could use some code here, factor integer 27720. Right, what do I get? Now what this gives me is gives me the primes first and the powers second, right? So, I mean, if this were some kind of open book exam, what is to stop me from just using this function, right? So you want to just demonstrate some steps that show that you know how that calculation goes.
Okay, cool.
Okay, Ariel, you say, can someone help me find the tutorial sheet? Can't seem to find it on Blackboard. Well, actually, come to think of it, they didn't give me a tutorial sheet. They just gave me a set of answers. So if you just give me a moment, I think I can probably share that with you in the chat, because I've taught this before, and so I keep these things handy in case someone else doesn't provide it. So I'm just going to open up one of my files. All right. So these are the things I taught last semester, except I remember, I think I've got 7861. Okay. Now, tutorial sheets. Okay, let's have a peek at this. Tutorial sheet 4. That's solutions. I don't want to give you solutions, because you're meant to try to work them out, and it's too tempting otherwise. So that's not quite the right one. So it must have changed a little bit in the weeks, because what we have is 12-week semester, I think, this time. So let's have a look at this one. This looks like the one. All right, Ariel, I'll see if I can give this to you in the chat here. So hang on. How do I upload something here? File, okay. Right, okay, so I want, where have I put this? On the desktop. Okay, this is the desktop, all right, so I'm looking for UQ courses. There we go. And that was Math 7861. And then tutorial sheets. And then I'll give you, that was number 5. Okay, so that should come up in a moment. But normally, Ariel, those should be in Blackboard somewhere. All right, so it's uploaded now. Did you get it? You can just give me a thumbs up. Yep, good, thanks. All right, so anyway, let's move on. So 4.1c, find integers q and r with r between 0 and d. Now this is a less than or equals to there, but this one is strictly less than, so that n is equal to dq plus r. So this is just the quotient remainder theorem. There should exist such integers r and q. Okay, so n is minus 95. So first we want to find the quotient, all right? So then I'll just take minus 95. I'll divide it by, what's the other one? 11. Okay, let's look at what that is. So we have minus 8.63. Now, remember, this is the greatest integer, so I think the floor is meant to be minus 9. It's a little bit tricky when they're negative. So, yeah, so I'll just use the floor function here just to double check that for us. Okay, minus 9, that's good. So just watch out when they are negative. Okay, so we want to round to the to the greatest integer less than or equal to. And it's a little bit tricky when it's negative. Okay, so what we find here is that q is equal to -9. Okay, so we've got that now. What we want next is the remainder. So -95, and then remember we subtract dq to get r. So d was 11, so -11, and then times the q, but q is -9. And this should be our remainder. Okay, so remainder 4. Remainder is 4. All good, guys? All right, okay, so let's have a look at 4.2. So 4.2, an integer n when divided by 7 leaves a remainder of 4. What is the remainder when 3n is divided by 7? Okay, so what we want to do is write this expression. Okay, so let's put n equals 7q plus 4. All right, and that's just the statement. That's the statement here. That's the first sentence there, right? But yeah, I would like that to be blue. It's not blue because I put that in memory earlier. Okay, anyway, so this is just a hand calculation that I'll do here. So the next thing I want to do is obtain 3n. Okay, so 3n will be just multiplying this by 3. So 3n is equal to, let's see, 3 times 7 is 21. So we'll have 21q, and then 3 times 4 is 12. All right, but we want to know the remainder when this is divided by 7. Okay, so can we see any ways that we can express this in terms of 7? Well, we should put that 12, write that 12 in terms of 7. So 7 plus 5 is 12. So I can write 7 plus 5. All right, now this part of it here is divisible by 7. Okay, so let's just put the 7 in front, factorize that out. And then when we factorize the 7 out, what we have is 3q plus 1. Okay, so good. Now I have something times 7 plus 5 is equal to 3n. So that tells us that the remainder is 5, and yes, that's between 0 and 6. So remainder is 5. Any questions? I think these are fairly easy so far. All good, great. Thanks, guys. Okay, let's look at the next one. Now, ordinarily, if I were doing a tut in class, I would just get you guys to do some of the problems, but I found that with online tuts, it just doesn't work so well as I'd like. So unfortunately, this is a little bit more like a lecture. Of course, I'd rather give you a chance to work on something and let me see where you go wrong. So please, please, while I'm doing this, do the calculations yourself with pen and paper, and see if you can, get your hands dirty and see if you can get the same results that I do. All right, so let's see, 4.2b, when an integer m is divided by 11. So I'm going to skip this one and come back to it later because there's quite a lot of problems here. So let's just start with the next one, I think. 4.3. Okay, so for the following statement about positive integers m, n, and q, if true, prove it. If it's false, give a counterexample. Okay, so this says if m divides into n and n divides into q, then m squared divides n times q. Okay, so we can just go about this via direct proof, right? Because it looks true, okay? So if you suspect it's true, then you want to start proving it. You have to select a method of proof. Now there are several for an implied statement, right? You could use direct proof, just using the premise and deducing the conclusion. All right, but you also have the contrapositive. So rather than proving P implies Q directly, you would then use a direct proof on not Q implies not P. And then there's contradiction. A proof by contradiction would have you assume that the premise is true while the conclusion is false. So that you're basically assuming that you have T implies F, right? Which would make the whole thing false. And you hope to come up with a contradiction. And if you get a contradiction, that says that the assumption T implies F was false. So the statement would be true. Okay, but this one will do this by direct proof. So then we're assuming that the premise is true. So given that m divides n, we can write n as, say, a times m, where a is an integer. And then we can also write q as b times m. Or sorry, b times n. That's what we have, n, because n divides q. Okay, and we have to show that m squared divides nq. All right, but to do that, given that we've got an expression for n and q, all we need to do is give an expression for nq. All right, so nq equals, let's see, we have am for n, and then we have q equals bn. Okay, but we also have an identity for n, so we can express this as am times b, and then n was am. All right, and then let's just write this. That is a squared times b times m squared. And so clearly, because we have something times m squared, that means that m squared divides nq. So next we'll say, hence, m squared divides nq. All right, I'm going to make this a comment here, and then I'll just write clear q so it doesn't come out black. All right, great. Any questions about that one? And then I can just show that again in bright blue. No, are you guys still here? All right, good. Jinyu's here. Okay, let's have a look at 4.4a then. So it says prove if k is any even integer and m is any odd integer, then the difference of these two squares is divisible by 4. All right, so this looks like we should also be able to do this by direct proof. All right, so let's just look at the first part of it. K is any even integer. Okay, if k is an even integer, then there will exist an integer a such that k is equal to twice a. All right, and also, if m is any odd integer, then m is equal to 2b plus 1. In other words, b exists as well. Okay, so given that we have that, what we want then is to simplify this expression here for the difference of these two squares. All right, so let's begin that. And I'll just do some substitutions here with what we have. So k is 2a, and we put m is 2b plus 1. All right, great. So we sub those in. Now we can simplify. All right, so you can see that's a 2 there, that's a 2 there, so we can factorize that 2 out and then square the 2. But when we do that, we end up with 2 squared is 4. So when we factorize the 2 out and then square, we have a 4 in front. And then we have inside the bracket a plus 1 squared. Okay, now let's simplify this second part of it, 2b plus 1 minus 3. So that's 2b minus 2. And then again, there's a 2 in the 2b minus 2. All right, so let's create another line. And I'll even move it down in case you can't see the whole screen. So we'll factorize the 2 out, and then it gets squared, so we have a 4 in front. And by now you can see that we are finished with that because this whole thing is divisible by 4, right? So in other words, I can put a big square bracket on the outside and factorize that 4 out. Okay, so what's inside that square bracket is an integer. So we'll say this is divisible by 4. Okay, good. So that one's done. Let us know if I'm going too quickly. All right, next one. All right, so prove the difference between the cube of 2 consecutive integers leaves the remainder 1 when it's divided by 6. Okay, so the first thing we need to do is construct the difference between the cubes of 2 consecutive integers, right? So n and n plus 1 are consecutive. So then we want to use n plus 1 cubed minus n cubed. All right, so this is the expression. And then we want to show that this has a remainder 1 when we divide by 6. Okay, so the first thing, the natural thing to do would be to expand and simplify this. All right, so when we expand n plus 1 all cubed, now this comes from, if you remember, Pascal's triangle. So in other words, we have n cubed and then plus 3 times n squared and then plus 3 times n and then plus 1. Okay, and then I want to subtract the n cubed that is there. And I'll put a bracket around this to make it clear that this was the first term. Okay, good. Now, next, let's make a new line and simplify that. So what we have now is we want to cancel the 2 n cubes there, this one and this one. Okay, so let's cancel those. And then we have 3n squared plus 3n. All right, now think about what we're aiming for because you can almost see it there, right? So it has a remainder 1 when it divided by 6, right? So there's a 1. Now, these both have a 3 in front, right? 3 and 6 have a common 3 in them, right? So we're nearly there. So our next step is to factorize the 3 out of those two terms. So let's do that. Factor the 3 out. Okay, and then we've just got to realize that this is even. Okay, so to show that it's even, let's factorize the n out of it also. All right, so now we have 3 times n plus 1. And now we need to write a little bit of English, okay? So something like, notice that n times n plus 1 is even, since if n is even, then we are done. If n is odd, then n plus 1 is even. Okay, and I need to make all of this a comment because I can see that Mathematica now wants to run a Wolfram Alpha window, which incidentally I can do from within this software as well as run Mathematica code. And I'll just give you an example here because I am connected to the internet, so I'll just show you what I mean. So I'll open a new cell there. And if I go equals equals, then I can ask a question like, who is Barack Obama? And Shift Enter, and it'll look that up. I can see I've spelled it wrong, but I don't think that matters. So it's basically Googling this, you see. Which is occasionally handy, but mostly I find this a little bit of a, it kind of gets in the way, this feature, because I accidentally press 2 equals. All right, so I'll cut this one out. And so it's found the right spelling. Okay, great. Any questions now? All right, so it's 12:30, so I guess we're about halfway through the session, and we're at question 4.5. Okay, so this one says, prove by contradiction. For all integers c, d, and e, if c divides d and c does not divide e, then c does not divide d plus e. All right, so I'm going to set this up, right? And so I'll give you a little bit too much information, but it's so that I remind you of how a proof by contradiction works in terms of what you've learned in logic. Okay, so what we do first is say, assume the statement is false. Okay, so what that is, so I'll just put in brackets. So note to self, recall T implies F is false. All right. So this is what we're assuming, right? That the statement is false. So we're assuming that we have a T implies F, right? And we hope to find that that leads to an absurdity, and so this assumption cannot be true. All right. So we assume then that the premise is true. So C divides E and C does not divide E, while the conclusion is false. Okay, now if we just negate this conclusion, then we have C does divide D plus E. Just give some space so it's easier to look at, while C does divide D plus E. Okay, now at this point there are a couple of different ways to argue or express what divisibility means, but I think I'm going to go for congruences. All right, so now let's see if I can open up. I don't know if it's there, but I'll look in the palettes for the congruent symbol, because then I can just copy and paste. Oh, there it is. So fine, great. Okay, good. So that's the congruent symbol. So then what we're saying is, then given this assumption that says that D is congruent to 0 modulo C, all right, and also D plus E is congruent to 0 mod C. And typically when you write this, you put a bracket around this. That's just typical notation for writing mod something. It might be nice to leave a little bit of space. And how about we even line those up? So what we're looking at here is we have a simultaneous congruence. Okay, and that's just this statement here, C divides D, and then the statement C divides D plus E. Okay, so given that's the case, you can think of these, or they act a lot like equations. So that's why it's a useful way to represent divisibility. So what I want to do then is replace in the second equation D with 0, because we can do that. So we have 0 plus E is congruent to 0 mod C. Right, but if you see what this says that E congruent to 0 mod C, and that means that C divides E. Hence, C divides E, comma, a contradiction. Okay, because it contradicts the assumption that C does not divide E, right there. Is that clear? Any questions? Oh, good. Thanks, Jin Yu. And again, just interrupt if something doesn't make sense. All right, Sanchez says, how does D equal 0? Well, it's not an equal zero, Sanchit. It's a congruent. You see, so this says that the remainder of D when I divide by C is 0. All right. So you see how that's the same as C divides D. If C divides D, then D divided by C is an integer. And so you can express that as D equals C times some other integer plus 0, where 0 is the remainder. Okay, so I've just translated the statement that C divides D into a congruent. So that's not an equal sign, it's a congruent sign. Yeah, that's right, equivalence. Yeah, well, yeah, congruence is probably a more common way to say this than equivalence. But okay, any more questions about this one? And you could do this in a different way, right? You could avoid congruence if you wanted to, but I just think it makes for a nice, simple way to, and clean way to obtain the contradiction. Okay, so let's move on and look at 4.5b. All right, so that says prove if y is any integer, when y squared is divided by 5, the remainder is 0, 1, or 4, but not 2 or 3. Okay, so in this one, you want to separate cases, right? So how many possible ways can you express the integer y in terms of the integer 5? Well, there are 5 ways, right? You can express it as 0 mod 5. You can express it as 1 mod 5, 2 mod 5, 3 mod 5, or 4 mod 5, right? But you can do even better here for the sake of the proof, because since we're going to square y, so we can separate exactly 3 cases. So let's write them out. Case 1, y divisible by 5. In other words, y, and I'll go borrow this congruent symbol again, y congruent to 0 mod 5. Okay, so that's case 1. Now case 2, copy and paste this, and then I'll change it. Y, and I'll just go straight for congruences. Case 2, y is congruent to 1 mod 5, and then we would increase. But since we're going to square this, let's combine a couple of cases, and I'll go and look for a plus or minus, because that's what I want here. All right, I see a plus or minus, good. Okay, so this accounts for y congruent to 1 mod 5 or y congruent to 4 mod 5, because that's the minus 1. Minus 1 is congruent to 4 mod 5. And so here I can say that the second case is y is congruent to plus or minus 1 mod 5. Does that make sense? Sanchith? Yep, okay, good. Now, case 3, and there's only one more case if we're including plus and minuses here. Case 3 is y congruent to plus or minus 2 mod 5. And now let's just note that we have all the cases, all right? So this one here, the second case includes 4 mod 5, and then the third case includes 2 mod 5, and it includes 3 mod 5. So that's all the possibilities, 0, 1, 2, 3, and 4 mod 5. All right, there are no other classes mod 5. Okay, so let's look at these cases one by one then. So in the first case, that y is divisible by 5, we can write y equals 5m, for example, right? And so then if we square that, so y squared is equal to 25m squared. Okay, so this has a remainder of 0, doesn't it? Because this is 5 times 5m squared. So we'll say this is congruent to 0 mod 5. Okay, Jinyu says reminder in case 3 is 4. Are you saying you would like a reminder or a remainder? Maybe you misspelled that. So, okay, so let's say we've done case 1 now, right? Everyone happy with case 1? And then we'll get on to Jinyu's comment. You follow case 1 here, Jinyu? Yep, okay, so case 2. Now this incorporates, okay, so let's rephrase here. This is assuming that y is congruent to 1 mod 5 or y is congruent to minus 1 mod 5, but minus 1 mod 5 is the same as 4 mod 5. And that's because 4 is 1 less than 5. Okay, so we're really incorporating both of those cases here. But it's nice to be able to do this with a plus or minus because the square of plus or minus 1 is 1. So that's why I've done that rather than written it this way. Does that make sense, Jinyu? Okay, great, good. All right, so what we do now is let's square this, right? So hang on, I just need to write y equals, well, it'll be 5m plus or minus 1 then, right? So there exists an integer m such that we can write y as 5m plus or minus 1. Okay, and now let's square that so that y squared is equal to this one squared, and then we actually square it, so we have 25m squared, and then the middle term is 5m times plus or minus 1. Now we're incorporating both cases here. So we also need the plus or minus 1, and the signs match. When it's a plus, and when it's a minus, it's a minus. So we need a 2 times m times plus or minus 1. So that's 10m. Okay, and then plus or minus 1 all squared is just plain 1. All right, good. So the next thing we want to do is phrase this in terms of multiples of 5, right? But it's clear by now because the first part of this is divisible by 5. So just factor that out. And then inside I'll have the 5 there and a 2 there. Okay, so we see that this is congruent to 1 mod 5, right? So just copy and paste that symbol. So in other words, y squared in this case is congruent to 1 mod 5. Okay, so far I've got a 0 mod 5, I've got a 1 mod 5. We're probably going to get a 4 mod 5 next in case 3. All right, so in case 3, what we'll have is, in this case, we will have y is equal to 5m plus or minus 2. All right, so there is such an m. And I should probably say that there exists an m such that y is equal to 5m plus or minus 2. And it's not necessarily the same as this m, right? Or this m. It'll be a different m. Okay, now we square this. So we have y squared is equal to the square of 5m plus or minus 2. Okay, and we expand that, and we have 25m squared plus or minus 5m times 2 again, so that it will be 20m, and then plus or minus 2 squared is 4. Okay, and now you probably see why I chose to write this in terms of plus or minus rather than separate 5 different cases. That's because it just makes this easier. All right, so we're almost done because we just need to represent the first part of this as being divisible by 5. Okay, so I'll factor the 5 out of this right here. So that's 5 times 5 in the first part, and then 5 times 4 is 20. Okay, so there exists an integer of this one such that y squared is 5 times that integer plus 4. And so what we have is that we've deduced that this is congruent to 4 mod 5. Okay, so that completes the proof here because we've used all of the cases and we only got out 0, 1, or 4 mod 5 as the remainders when we divide y squared by 5. Any questions? Oh, good. Okay. All right. Sure. 4.6. Prove or disprove for all integers a, b, c. If a divides b and a divides c, then a divides 4b minus 2c. Okay, so if we actually have a dividing b, then we can express b equals a times some number, let's just call it k1. Okay, so we're going for a direct proof here. And likewise, c is equal to a times some k2. All right, so now what we want to do is take this one and sub in. Okay, so I'm just replacing the b with a times k1 and the c with a times k2. And then we'll simplify and we'll find that there's a factor of a involved. Okay, so we'll factorize out the a. It goes in front. And then we'll say, comma, which is divisible by a. Okay, so that completes the proof. And that's fairly simple. All good? Okay. All right, 4.6b, prove or disprove. For all integers a, b, if a divides b, then a squared divides b squared. All right, so I think we can use the same technique here. So let's put b equals k times a. All right, then we square both sides. So we have b squared is equal to k squared times a squared. And straight away, we see that a squared divides b squared because b squared is equal to some integer times a squared. So we'll say, so the result follows straight away. And that's an easy one. All right, just stop me if you've got any questions. Otherwise, I'll just keep going. Okay, 4.6c, prove or disprove. For all integers a, b, c, if a divides b, c, then a divides b or a divides c. All right, so this one isn't quite true. And the reason you can, well, you just choose composite numbers and find a counterexample, right? So one that comes to mind, I guess, is if you put a equals 4, b equals 6, and c equals 10. Now I've chosen that carefully because right here I have something that goes into parts of each of them, right? Okay, so what we see then is that a divides 6 times 10, which is 60. So in other words, 4 divides 60, but 4 does not divide 6, and 4 does not divide 10. Okay, so this one's false, and we've given a counterexample, or an example of it being false. All right, let's continue. All right, now the next one says, assume that a, b, c, and d are integers. Find a condition on these variables that ensures x is a real number, where this expression, okay, sure. So now, if we do have this expression being met, then we can express that as ax plus b is equal to 2cx plus 2d, right? Just multiplying both sides by cx plus d. All right, now if we're aiming to solve for x, then we would want to collect like terms, right? So next we would write a, taking the cx, the 2cx over to the left-hand side, and then factorizing out the x. So we would have a minus 2c, and then x, and then that would be equal to 2d minus b, taking the b over to the right-hand side. Okay, so now we see that condition, because in order for x to exist, satisfying that, what we need is for a minus 2c to be non-zero. Okay, so need a minus 2c non-zero. Okay, and given that it is non-zero, the question then asks us, and I don't think I wrote this here, no. The question then asks us to show that x is rational when you do have that condition met. Okay, so then if we just divide by a minus 2c in this expression, then we get that x is equal to 2d minus b all over a minus 2c. All right, comma, which is rational because a minus 2c is non-zero, and all of these a, b, etc. are integers. Okay, good. Now it's 12:52. If you need to get somewhere, go for it. I think I'll just continue and do a little bit more until the end of the hour. But yeah, feel free to just drift off to your next responsibility. Okay, so next one, 4.7 BI. Prove or disprove, for all real x, the floor of x squared is equal to the floor of x all squared. So this is the greatest integer less than or equal to, say, y, where y is the function inside. All right, so this one is false, because you can just take a counterexample rather immediately. For example, if we just choose x equal to 1.5, then the floor of 1.5 squared is equal to the floor of, let's see, 1.5 squared. 15 times 15 is 225, so this is 2.25. And now if we take the floor, well, that's 2, isn't it? Whereas if we look at the same thing on the other side, the floor squared, the square of the floor of 1.5 is equal to the floor. So the floor of 1.5 is just 1. Okay, thanks, Ariel. I'll see you next time. Yeah, you're probably gone by the time I'm seeing this, but thank you. Okay, so floor of 1.5 is just 1, so we've got 1 squared. And 1 squared is 1, and so 2 is not equal to 1, right? And so here we have a counterexample. Righto, let's have a look at the next one. Now, prove or disprove. So this one here, for all integers n, the floor of n squared divided by 4 is equal to n minus 1 over 2 times n plus 1 over 2. Now that looks like it should be false given the previous one, but it's true. Okay, so let's give a proof of this. So, okay, so the floor of n squared plus 2. Now we're told that this is odd, right? So we'll put n equals 2m. I'm really having trouble with my fingers. Okay, 2m plus 1. So that characterizes it as being odd here. Okay, so then the floor of n squared over 4, just subbing in, we have 2m plus 1 all squared over 4, so we'll simplify that. And so the square of that, we still want a bracket, but the square of this is 4m squared plus 4m plus 1. Okay, we're nearly there. So now we want to divide that 4 in. So when we divide it in, we get, this is 1/4, and then we divide the 4 here. Okay, so now I'll put a bracket around this 1/4 to say that one's not an integer, but these two are integers, right? Given that m is an integer. All right, so now this is like having, so 5.25, for example, and then taking the floor. So in other words, the floor of this, when you have integers inside your floor function, you can just pull those out straight away. Okay, and so it's just that integer part plus the floor of the non-integer part. All right, and that's easy now, right? Because this is 0.25, so the floor of 0.25 is 0. And so this is just m squared plus m, right? Now let's have a look at the right-hand side, because that's just the same, or at least it's meant to be. Okay, so this is, now we sub in n equals 2m plus 1 in each of the n's there. And then we just simplify, and we'll see that it's the same. Okay, so 1 minus 1 is 0. And then this is 1 plus 1 is 2. Okay, and then what we have is just, this is just m. 2 divided by 2 is 1. And then this one is m plus 1, isn't it? Okay, and then you expand that and you get m squared plus m. And you see that those two are the same. All right, great. So we got 3 minutes. Let's see if we can knock this one out in 3 minutes. So prove that there's a unique prime of the form n squared plus 2n minus 3, where n is a positive integer. All right, so the first thing you want to do is factorize this one, all right? Because if you can factorize it, then you can see how it could be composite or not composite. All right, so if we're going to factorize it, then we have n plus something in there and n plus something there, right? But the factors of 3 are 1 and 3. Okay, but we've got a minus sign there, so we need to choose the appropriate sign, and we choose that by looking at this. So it's that's positive, so we'll put a minus sign here. Okay, and that expands out to be this left-hand side, so that's the correct factorization. But now we're told that n is a positive integer, right? And if we're looking for primes out of this, well, then the smallest one would have to be equal to 1, right? So this equals 1 times n plus 3 when prime. Okay, so if this one here is 1, then that says that n minus 1 equals 1, so n equals 2. So n is 2. Great, so now if n is 2, then this expression here is 1 times 2 plus 3, so 5, right? Which is prime. Okay, so there exists a prime that comes out of that. Now we have to do uniqueness. So to show that that's unique, you just observe that. So observe or notice that, spelled that wrong. This is composite otherwise, because we have a product, and it will be 0 when n is equal to 1, or n minus 1 greater than 1 otherwise. Okay, just move that to a new line. All right, so it's 1 o'clock now, so I'll just talk about this one briefly. suppose we change the quadratic to this one. Is the conclusion the same? Well, no, it's not, because this one now is irreducible over the integers. And in fact, if you factor this, you just either have real numbers or complex numbers. I can't see straight away, but yeah, so they're not integers when you try to factorize that. So the conclusion is not the same. And in fact, with this one, what comes out are primes or not primes, and you can get multiple primes out of it. So, and I can just show you a list right here while we're at it. So actually, you know what? I think I did that a moment before. So right here, just copy and paste that in. So here I just wrote some code. This just shows you the first one is the number n, and the second one is when it comes out prime. So there are lots of primes that come out of this one. Okay, thanks very much, guys. I know I went over time a little bit, but I covered the whole thing except for that one question at the beginning. So I feel okay about that. All right, thank you, and I'll see you next time.